for having me and for coming to part 2 of this tutorial. So today we're going to continue, and just a reminder of where we are in this. So in the first part yesterday, I introduced many questions about Borel sets, measure, category. And the goal for today is to talk about reverse mathematics, which is a framework in which one can place these questions. These are sort of informal questions. We can make them more formal by placing them in this framework. And then next time will be what's known so far. And I think I last time probably should have mentioned this, which is that I don't actually know the answers, even within this framework, to most of the questions that I asked in the first day. So just to place expectations where they should be. What's known so far is more like miscellaneous items. All right, so what we're going to do today is, so first I'll introduce what is reverse mathematics. There is a particular axiom called arithmetic transfinite recursion that's going to be really relevant for what we do. In reverse mathematics, one important idea is you want to show when one axiom is not able to prove a theorem. So we'll go over how you do that. And then the rest of these items, I think, will make more sense after I've done them. So just some more things, how you represent Borel sets in this reverse math context. All right, and so then just as a reminder also of what we did last time, so we looked at several theorems of mainly from Borel combinatorics. And some of those theorems we were able to prove using a category method, and other of those theorems we were able to prove using a measure-based method. And sometimes they could be proved using both methods, but sometimes only one method worked, and we wanted to know if the other one could. And sometimes there was not even any known proof by either of those methods. So in those situations where let's say a proof by measure is known, but a proof by category is not known. Well, you could keep trying, just keep looking, try to find a proof by category. Okay, or you may think that maybe it's not possible. So if it's not possible, how could you tell? So reverse math is a framework in which we can place that kind of question. The idea behind reverse math is we want to make a mathematical model of all of mathematics. Maybe not all of mathematics, but we want to make a mathematical model of like a big part of math. And then within that model, figure out what can and cannot be done. So it turns out that most math can be carried out in the context of second order arithmetic. So in second order arithmetic, we imagine that everything that exists is either a natural number or a set of natural numbers. Now, this seems like a very impoverished mathematical universe, but it turns out that a vast majority of math can be represented in this way, outside of some topics in set theory, because of the fact that we can use coding, right? So a subset of the natural numbers, we could think of it as an infinite sequence of zeros and ones. And so anything that you want to encode using bits, we can talk about in the context of reverse math. So any kind of functions or even Borel sets. When we communicate what is a Borel set, then usually the way that we do that is we say, okay, well, here's how you build it out of smaller sets using countable unions and intersections and so on. And so you have a tree, which is a countable object that the tree is just telling you like the ancestry of the Borel set. So you can say, how did I make my Borel set? Well, here was some open set, and here was some other open set. And I took those countably many open sets and I intersected them all together. And then I had some other Borel set that I made somehow, and I had some other Borel set that I made somehow. And then I union them all together. Okay, so this whole thing, this history of how to make the Borel set, I can just represent that using an infinite sequence of zeros and ones, and so that's how it appears in this reverse math second order arithmetic situation. All right, so we say that we're going to imagine that just natural numbers and infinite bit sequences are all that exist, and then there are a number of axioms. Now, I could make a slide that just says, okay, here's all the axioms of second order arithmetic. I don't usually find those slides to be like that informative, personally, because I can't absorb that many axioms like in the course of a talk. So instead, I'll just say that the axioms that we assume are basically, there's axioms about how the first order part works. So the numbers have to satisfy things like they have to be addition has to be commutative, multiplication has to be commutative, and sort of other things that you would expect to make natural numbers behave the way they should. And then we also have axioms that that tell us which infinite bit sequences are actually required to appear. So for example, there's one axiom that says that if there's an algorithm to compute a certain bit sequence, that sequence has to exist in our model. And then there's other axioms that tell us when other sets have to exist. And I'll give a list of the common ones in a moment. All right, so in this context, the sort of slogan of reverse math was stated by Friedman, who's along with Simpson, one of the founders and developers of this system. Said when the theorem is proved from the right axioms, the axioms can be proved from the theorem. All right, so what this means. Suppose that you have a theorem, and so the axioms of second order arithmetic, whatever they are, I didn't tell them to you, but they're strong enough to do most of them. All right, so let's say that you've used these axioms, you've proved a certain theorem, and along the way of proving that theorem, you used some particular axiom, let's call it axiom A. And now you're wondering, all right, but is there a different proof of this theorem? Is there a way perhaps to avoid the use of axiom A as a proof? Well, one thing that you can do is reverse, and this is where the name reverse mathematics comes from. You can reverse the role of the theorem in the axiom. You can say, all right, what if I start by thinking of the theorem as if it's an axiom, and I don't assume the axiom anymore? So starting from the theorem, and maybe I'll assume a few like small axioms, which on this slide here are called a base theory. So pick some few small axioms that are just enough so that the theorem makes sense. But don't include axiom A in that collection. And just take those few axioms in that theorem and try to prove axiom A back. And see if you can succeed. So what happens if you succeed? Well, if using the theorem and the base theory together, you're able to reprove the axiom, then that sort of tells you that the axiom was needed for the theorem. Because by contraposition, if the axiom is false, then the theorem would have to be false too. So this is the idea behind reverse math. Now, let me just say a couple more words about this base theory. So if you throw away literally all of the axioms and just say, I'm only going to use the statement of the theorem to try to prove back the axiom, then you're going to probably be in some kind of nonsense land. Like there's just not enough for like things to really make sense. So to start ourselves off, we say, basically, we're always going to assume that addition and multiplication are commutative. We're always going to assume that any time that we have an algorithm that can produce something, that something is going to be guaranteed to exist. So this is basically like a base theory which consists of roughly computable mathematics. So you think of anything that you can sort of do computably, we're going to say our axioms declare that we're allowed to do that in the course of a proof. And then all of the theorems and axioms that we're going to be interested in measuring their strength of, these are theorems and axioms that somehow require us to go beyond constructive mathematics in order to carry them. So one example of this, if you remember from last time, we finished up by taking a look at the proof that every Borel set has the property of bearing. And one of the things that we were looking at in that proof was we were noticing that if you wanted to go through that proof and actually produce all of the objects that the proof needed, you might have to use like a halting step, right? You might have to take a jump, you might have to take another jump. And so that's sort of a non-constructive thing. Right, so let me pause here for a sec and say what I also meant to say at the beginning of the first tutorial, which is I welcome questions at any point. So if you, as you're listening, you have something you want to go back or any question that you have, just get my attention, and I would be much happier to know that something is needs to be better understood and do it in the moment than just have everybody be lost in some way. So please don't hesitate. All right, so this is the idea behind reverse mathematics. So what are some of the common axioms that are used in this system? So Right. So as it's stated here, there are some things that are like the axioms of second order arithmetic. And then there are other things that are the theorems, the things that are not axioms, but the things we're interested in. However, what we actually do with them is we sort of blur the distinction between a theorem and an axiom, right? Because we say, all right, other than the space theory that never changes, well, almost never changes, sometimes we're going to be assuming the theorem and trying to prove the axiom. So really, instead of thinking of everything as like theorems and axioms, really we just think, okay, well, there's a whole bunch of mathematical statements. And some of them, if you assume them, you can prove other ones. And that's really the structure that we are going to be exploring. All right, but as people started exploring that structure, what they found was that if you look at many theorems of ordinary mathematics, many of them actually cluster. And they cluster into what's called the big five systems. So it turns out that a lot of theorems can actually just be proved using only constructive methods. So anything that can be proved using only the base theory is sort of in this category. Then there's another axiom that we won't use much today, but that essentially corresponds to the idea of compactness. So you've probably seen a proof that the unit interval is compact. You've probably seen proof that, let's say, like every continuous function on a bounded interval attains its maximum. And that proof uses the compactness of the unit interval. But if you assume that every continuous function on a closed interval attains its maximum, then you can actually, using that as an assumption, you can reprove that the unit interval is compact. So that would be an example of two theorems that are, in this sense, equivalent to each other, and they're both equivalent to this Koenig's axiom, which then you don't need to know, but just sort of giving an example here. All right, so an axiom that we will talk about today is the what's known as the arithmetic comprehension axiom. And what this axiom says is, suppose that you can take a set of natural numbers that you are describing using a sentence of this form. Right? So what this sentence is, you take some computable predicate, and then you just have finitely many quantifiers over the natural numbers. Right? So you have some description, and I'll show you an example on a very student slide of a set. The arithmetic comprehension axiom tells you that there's an axiom that guarantees that this set actually exists. Arithmetic transfinite recursion, another axiom we'll talk about quite a lot, so I won't talk about it anymore right now. And then power comprehension is sort of a similar thing. If you can describe a set in a certain way, but now the way is more complicated than this axiom says that the set exists. All right, so this is just kind of the backbone of what we might call the reverse math universe, and you find theorems of ordinary mathematics equivalent to each one of these principles.
Can I ask a question?
Yes, please.
How about induction?
Say again?
How about induction? Do you have full induction in all of them, or what is how much induction do you need?
Yeah, so within RCA, we include sigma 0, 1 induction for the natural numbers. Once you assume ACA, then you'll get the full induction, like the full piano axioms. And there's not included in the sigma 1 or power 1 induction. You have to assume those if you want them. All right, so let's talk a little bit about this axiom, ACA. So I've rewritten it, what the axiom says. All right, so recall from last time the Turing jump of x, which is denoted by x jump, is just the halting problem relativized to the oracle x. Right? So you have a set x and you're using it as an oracle to do the halting problem. And I want to talk about the theorem that for every x, the jump of x exists. Now, in the reverse math context, when we prove this theorem, we prove it using the axiom ACA. And the way that it's proved is exactly as written here. What is the definition of x jump? Well, x jump is exactly those numbers m, such that the mth algorithm of oracle x stops. if I want to be even more specific about what it means for the nth algorithm with orbital x to halt, I could write it out like this. There is some length of time so that the nth algorithm with orbital x halts within that length of time. All right, so the significance of writing it out this explicitly is that this part now that's within the parentheses, that is now a computable vector, right? Like if I give you x, if I give you access to x, I give you m and I give you s, and I just ask you, all right, does the nth algorithm stop within s steps with this orbital? You can literally just simulate it for s steps, and then you'll know the answer, right? So there's an algorithm that can do that. All right, so when I write it in this way, then I see that the collection of that the set x jump can actually be described using a format, which is the same format that ACA like guarantees that anytime that you have a set that can be described in that format, then that set will exist. All right, so the axiom ACA is what tells us that for every x jump always exists. All right. Did we really need ACA as an axiom in order to show that for every x, the jump of x exists? Well, at least according to the reverse math philosophy, then we would say, yes, we really needed to use ACA. And the reason is because if we just restrict ourselves to the base theory, but then add for all x jump exists as an axiom, then we're going to be able to get ACA as theory. All right, so this is not like a full proof, but it's just sort of an example, proof by example. All right, so let's take a particular example of a set that we might want to show exists. So consider the set y, which is the set of all numbers such that 2 times that number is the difference of 2 primes. Okay, so I picked this example because I think, as far as I know, at least, it's not known whether this set is everything or not. I guess people have sort of checked, like, for every even number, like, is it the difference of 2 primes? And kind of as far as people checked, I think they found that it was sort of heuristically, maybe it should be, but I don't know, maybe there are some exceptions. So this is some set, and also because of the fact that you have to like check all primes, you know, if you just haven't found one yet, you kind of never know whether you're going to find like a difference in primes or not. So this set, you know, it might not be empty. It might not even be computable. I mean, who knows? All right. So here's some set. Now let's say that I want to show that this set exists using the fact that the jump exists. Well, first we would use the fact that for every x jump exists to just tell us that 0 jump exists. So remember, 0 jump is just the halting problem relative to nothing. Then the axioms of RCA say that anything that we can do computably exists. So anything that is term reducible to 0 jump by RCA exists. And then finally, we can argue that this set y is term reducible to 0 jump. And the reason, just because, all right, you know, let's say you have a number m and you want to know whether it's in y or not. Well, you could write down an algorithm that says, all right, start looking for primes whose difference is 2m. And then you could ask 0 jump. Well, does that algorithm ever stop when it finds one? All right, so that's just one example. You could do this for every single formula, and then you see that ACA follows from this for all x jump exists. And so for that, we sort of say, all right, ACA was really a needed axiom, at least from that computational standpoint. All right, so let me next talk about another axiom on our list, which is the axiom of ATR. So ATR stands for, actually, I've not written it on this slide. ATR stands for arithmetic transfinite recursion. And the idea behind this axiom is as follows. So suppose that we have some linear order. I want to define on that linear order what's called a jump hierarchy. So intuitively, so before I get to this most general definition, intuitively the idea is that I have a linear order, and maybe I'll think of a linear order that has order type omega plus 1. Right, so here I've got something order type omega, and I've got something there at the end. So by jump hierarchy, what I mean is to this least number, I'm going to assign with 0 jump. And then to the next one, I'll take the jump of what I had previously. And then to the next one, I'll take the jump of what I had previously. And keep going. Sorry?
The slide moved.
Oh, the slides are moving. Thank you. All right, so let's put that down. Right, so as I go on in the linear order, every time that I have a successor in the linear order, I want to take a jump. And anytime that there's a whole bunch of stuff, like before a certain point in the linear order, somehow I want to take all of that together, right? To take this whole thing, like whatever that is, and represent that as like a single thing, and take a jump of that. Right, so whatever this thing was, I'll take it and I want to take its jump to get at the next point. All right, so what I've drawn up there, what I've drawn up here is sort of the typical case where you would want to use a jump hierarchy, where you have an order. But you can actually define the concept of a jump hierarchy for an arbitrary linear order, and that's what's done here. So a jump hierarchy on a linear order X is just a function that assigns every element of the linear order some value. And those values are supposed to satisfy the property that if I look at the value of the function at a particular point, then the thing that comes out should be what you get if you take whatever the function had for everything that was less than that value, encode it in some like natural way so you can use it as an oracle, and then take the jump of it. All right, so a linear order is called a well order if it has no descending sequence. So your ordinals are your canonical example of these. And if you have a well order, then it's clear that you can make a jump hierarchy on it because you can just go along by induction. Or just say, all right, every time there's a well-defined next form, and I can always just take the jump of everything that came previously. But the definition doesn't require X to be a well order. There could be some linear orders that are not well orders, but just happen to support a jump hierarchy. Like maybe for no reason, but it just so happens that you can assign sets to it in a way that this works out. So keep that kind, even though the well order is sort of the first good example of a jump hierarchy. Keep in mind the possibility that it could happen on non-well orders. All right, so arithmetic transfinite recursion is the statement. For every well order, a jump hierarchy on that well order exists.
X is countable.
Say again?
X is countable.
Yes. So and everything is countable in this reverse map because we only have the natural numbers and then the subsets of the natural numbers. Okay, so this idea that we are going to sort of iteratively take jumps along the well order has already appeared without all of these fancy terms in the previous talk. So remember when we proved that every Borel set had the property of bare. I drew a picture, which I'm going to not exactly draw again, but I'll draw a similar one. So if we wanted to show that every Borel set had the property of bare, what we did was we had this tree that represented the whole Borel set. And then we were able to say, all right, if you want to come up with, like, for every node in that tree, an open approximation to the set, like that's just below that node, you might need like some number of jumps. And if you want to go higher in the tree, you might need to jump again and again and again. So the thing that we were building, which let me just start drawing again, was actually the start of a jump hierarchy. Right? So suppose that I've got a Borel set that. So I'm not going to really label the intersections or unions or whatever, but just there's sort of something happening that potentially requires a jump at each stage. So maybe we had like down here like some open sets that were naturally open, so their open approximation was just didn't need anything to compute it. Maybe at the next level we needed zero jump to compute. Maybe at the next level we needed zero double jump to compute what's the open approximation of the set that's just included by this part. But now imagine up here, let's say maybe I've got a union here. Let's imagine that what if this set actually took 3 jumps in order to get its open approximation. And what if this set actually took 4 jumps in order to get its open approximation? And so on and so on. And what if I were taking an infinite union like that? Well, in that case, because of the fact that a Turing jump strictly increases the computational power, there's no finite number of jumps that would actually be enough to tell you the, sort of what's in all of these. So like if I wanted up here now to make the open approximations like the union of all the open approximations here, I'm actually going to need something that's even more powerful than any one of those finitely many jumps individually. So up here I might need something, so I'm going to go ahead and give a name to this guy, which is the omega plus 1 jump. We skip omega for some technical reason, which I don't want to talk about. So that is the amount of jumps that we might, in principle, need in order to do something at this level. All right, so imagine that we have ATR around this axiom. ATR tells us that anytime that we have a well ordered, we can always find a jump hierarchy on it. Now, this is a little bit more complicated object than a well ordered. It's actually like a tree, all right? But it's similar enough to a well ordered that ATR can also make some kind of jump hierarchy on it. So if you have ATR, then you can conclude that every Borel set is measurable and every Borel set has the property of Baire, and all the details, of course, having been concluded also. All right, so a natural question that we can now ask is, was ATR really necessary to prove these theorems? Or might those theorems actually follow from some simpler axiom? Or thinking of the theorems themselves as potential axioms, you could also just ask, all right, are these theorems just simpler than ATR or not? Because here's the thing, right? Our goal is to distinguish a method of measure from a method of category. Imagine for a moment, what if, assuming that every Borel set is measurable, what if I were able to reprove ATR? Well, if I could use every Borel set as measurable and prove ATR, then using ATR, I could prove that every Borel set has the property of Baire. And the other way would work as well. What if every Borel set has the property of Baire were able to prove ATR? Well, then using ATR, I could prove every Borel set is measurable. Right, so if these guys both prove ATR back, then according to reverse math, all 3 of those things will just be the same thing. And so reverse math would not be able to distinguish them one from the other. So what we're hoping, of course, therefore, is we're hoping that they're different, right? So we're hoping that ATR is not necessary to prove these theorems, because only when ATR is not really necessary will we have any hope that those measure and category are actually different from each other in this string. All right, so we have 2 things that we want to show are actually different, right? So we've already seen some examples of how, if you want to show that 2 theorems in reverse math are actually the same, how you do it, right? You assume one, you prove the other, then you assume the other, you prove the first one back. What if you want to show that they're different? Well, for that requires something known as a separation. So providing a separation means providing some model, right? So some collection of numbers and sets of numbers that satisfies the axioms of the base theory and satisfies the theorem, but which does not satisfy the axiom. Right? So in other words, we want to come up with, so right, in this case, we want to show that every Borel set has the property of Baire. We want to show that that does not imply ATR. So that means that what we want to come up with is a specific example of a collection of stuff that satisfies the base theory and satisfies the every Borel set has the property of Baire, but where ATR is false. If we can come up with such a thing, then we will know that the every Borel set has the property of Baire would not be enough to imply ATR, because there would be a context where the Borel set having the property of Baire is true, but ATR is still failed. All right, so what do these separated models look like? So the axioms of second order arithmetic actually don't guarantee that the natural numbers that we use are the true natural numbers. However, for simplicity, the most natural kind of model that we would like to create is one where the natural numbers are actually the true natural numbers. So let's just assume that that's always the case for our purposes of separation here. All right, so an omega model of second order arithmetic is the model where the first order part is the true natural numbers. So if we've decided that the first order part will do that, then the only thing that remains to specify in our model is, okay, which sets actually appear as the subsets of natural numbers that are said to exist. So in order to specify an omega model of second order arithmetic, we only have to give the second order part. So this is just some subset of the set of all possible bit sequences. And those will be the ones that we say exist, and maybe in the real world there's some other ones, but in our model, they're not. All right, these are the simplest, often used for separations. All right, so let me show you a couple examples of this. All right, so the simplest omega model is the omega model whose name is rec. All right, so rec stands for recursive, and it's just the set of all computable sequences. So if we imagine that the mathematical universe actually only consists of natural numbers and computable sequences, then in fact, it turns out all the axioms of RCA are satisfied. All right, I didn't list them all out for you, but basically, again, they're just the axioms that say the natural numbers sort of do what they should do. And then there are the axioms that says that anything that you can do computably exists. All right, so that's an example of an omega model that satisfies the basic. But in that model, it's not true that for every x, the jump of x exists. Right, so for example, the jump of the empty set does not exist in rec, because the jump of the empty set is not a computable set. So that theorem, for all x jump exists, is false according to rec. So this shows that ACA, which was the theorem equivalent to for all x exists, actually does not follow from RCA. This is a model where RCA holds, but ACA fails. So that shows that RCA cannot imply ACA. Let's do another one. All right, so a set is called arithmetic. If, right, so actually, technically, this isn't the definition, but it's the equivalent definition. Set is called arithmetic if it is term reducible to some finite number of jumps of the empty set. So let's consider the omega model, which is called arith, which just consists of all of those sets X that are arithmetic. Right, so this is a bigger model than rec. It's got more stuff. So arith is big enough that it satisfies ACA. And the reason for that is just if you have something that's term reducible to n jumps, then if you take the jump of it, or if you take the jump of both sides, then the term inequality still works. So everything that's in arith, this jump is also in arith. So this arith is an omega model that satisfies ACA. However, ATR is not true in this in arith. Why is that? Well, remember, ATR is the axiom that states that anytime that you have a well order, you have a jump hierarchy on that well order. So there is a computable linear order of type omega plus 1, right? So that's the one that I drew on the top of the border. So you can represent that linear order in a totally computable fashion, right? So already, even in rec, you have that linear order existing. It's a well-founded linear order, doesn't have any infinite descending sequence. But if there was a jump hierarchy on it, then this very last set here in the jump hierarchy would have to be strictly stronger in computational power than all of these guys. But everything that's in arith is strictly less in computational power than one of these guys. So that means that this 0 to the omega plus 1, that's a set that HER says has to be there. But in arith, it's not there. All right, so arith is an omega model in which ACA holds, but ATR fails. And so that shows that ATR is strictly stronger than ACA. All right, so there's our method for showing that one principle cannot prove another one, is to create a model that shows the separation. All right, so let's move on now to a topic that's really closely related to jump hierarchies, and that's the topic of hyperarithmetic sets. I think I've already sort of discussed this a little bit, but just to be really precise, I have some linear order. That linear order being computable just means that there is an algorithm which, given some pair of numbers, tells you whether or not the nth, like element of the domain in your linear order, whether one is less than the other or not. All right, so a set is called hyperarithmetic if it can be computed by f for some f, which is a jump hierarchy on some computable well order. Right, so you can think of the hyperarithmetic, and this is sort of where their name comes from, as like a really vast generalization of the arithmetic sets. So once again, coming back to this picture, if the arithmetic sets are the sets that are computable from one of these like first finite numbers of jumps, the hyperarithmetic sets are the ones where, well, if you compute it from this, then it's also hyperarithmetic. But you could continue this well order, continue the jump hierarchy going. And any set that you can get that way, anything you can compute from it, is called hyperarithmetic. Now, in the ordinals, of course, we can keep on going forever, like indefinitely. But when we're computing hyperarithmetic sets, at a certain point, we do have to stop. And the reason we have to stop is because in the definition of hyperarithmetic, we restrict ourselves to computable well orders. Now, if a well order is computable, there's an algorithm that's keeping track of it. There's only countably many algorithms, so there's only countably many computable well orders. So there is actually a limit. There's a least ordinal that we can't get to. But for all of the ordinals up until that point, we can take more and more and more jumps in this jump hierarchy, and then anything computed from any of that is hyperarithmetic. Is there a question? No, just...
So actually, kind of. So it's so f is a jump hierarchy. This is a function from or how do you?
Yeah, thank you. I am definitely abusing notation a little bit here, so thank you for pointing that out. So when I define a jump hierarchy as a function from the linear order to a set, that function I can represent itself as one big set, which is a set of like pairs of element of linear order, comma, a set. And then that entire object, you can actually also just like encode that as a bunch of bits. Like maybe in the first column, you have, like, imagine all your bits as arranged in a square. And then in the first column, you have the zero jump. In the second column, you have the zero double jump. So there are ways to encode it, and that's why I'm sort of allowing myself to abuse. Yeah, thank you for asking that. I keep putting the thing down. Should not put it down. All right, so these are the hyperarithmetic sets, and we've already mentioned that these do strictly extend the arithmetic sets. All right, so now's a good moment also to introduce another computability concept called relativization. You've already seen it without it being called that. So anytime that we have a computation or an algorithm, we could give the algorithm an oracle if we want to, but the algorithm can just freely use. So for example, earlier yesterday, we said that a set was computable relative to B, where it was computable from B, if you can get A out when you have a machine that has B as an oracle. So relativization is the word for give every computation in sight access to some oracle. So let's take now the definition of hyperarithmetic and relativize it. So we'll say that a set A is hyperarithmetic relative to B. If A becomes hyperarithmetic, once you imagine that every computation in sight just got to use a B oracle. Right? So the well order, instead of being computable, there might be an algorithm with a B order that computes the well order. Maybe that allows it to get longer. And also, every time you take a jump, B is somehow sneaking in there and participating in what the halting says. All right, so you just put this B in everywhere, and if you do that, then you get a notion of a sort of an extended computable reduction. It's a stronger contrarian reduction. If this happens, if A becomes hyperarithmetic once you relativize to B, then we'll say that A is hyperarithmetically computable from B, and we'll write that this way. All right, so for example, the omega plus 1 jump is hyperarithmetically reducible to 0 jump. Right, so things that are really powerful from the ternary perspective can still be like hyperarithmetic the same, because this is just like a much more powerful process to use. All right, and in fact, if we put a hyperarithmetic thing as the oracle, and then do any like jump hierarchy on that, then the thing that we end up with is still hyperarithmetic. So it's a class that actually has like a lot of closure under this jump hierarchy.
Another question.
Yes.
Is hyperarithmetic reducible transitive too?
Yes. Yes. Exactly. All right. So here's another omega model that you might want to consider, and that is hype, which is the collection of all hyperarithmetic sets. So the fact that we just talked about from the previous slide, that if you even if you relativize to a hyperarithmetic set and then take jump hierarchy, the jump hierarchy is still hyperarithmetic. That tells us that basically it sort of seems like ATR should be true, right? Because take any hyperarithmetic low order, take any jump hierarchy, like even using that low order as an oracle, the jump hierarchy has to be hyperarithmetic, so that jump hierarchy is in there. So it seems that ATR should be satisfied, but there is a catch. ATR is actually not satisfied. And here's the reason. All right, so here I've just rewritten ATR. ATR says for every well order, a jump hierarchy on that order exists. So here's the problematic fact. There is a computable linear order. It's not a well order, but it has no hyperarithmetic descending sequence. All right, so if hype is our model, everything about what's true and not, it's the truth according to hype. It's not the truth according to us. All right, so according to us, this linear order is not a well order, but according to hype, it has no hyperarithmetic descending sequence. So as far as everything that hype can see, it has no descending sequence at all. So a linear order like this, we call it a pseudo order, and hype believes that this pseudo order is actually a well order. So this weird non-well order, it might have a jump hierarchy, like just randomly, like in the real world, it might actually have a jump hierarchy. But that jump hierarchy is not going to be hyperarithmetic as it happens. It'll be like a really complicated and weird. So that means that according to hype, ATR is not satisfied. Right? All the real well orders have jump hierarchies in hype, but there are also these fake well orders inside of hype that inside of hype do not have a jump hierarchy. All right, so that means that if we have an omega model of ATR, it actually, well, it has to have everything in hype in it, because the things from hype are the things that are made from real jump hierarchies. So those real jump hierarchies are there. So if your ATR is true, then everything from hype is going to have to be there. But ATR is also telling you that for every one of these weird well orders, either you have to add a descending sequence, there has to be some set that produces a descending sequence, or there has to be one of these weird sets that just puts a jump hierarchy on this strange linear order. So anytime that you have an omega model of ATR, hype, all the sets from hype have to be there, but it's a strict inclusion, right? It has to be more stuff also. All right, so what are the strongest non-constructive theorems and axioms that we've used in our proof? I already mentioned that this is just to review. Every real set is measurable, every real set is perfectly fair, arithmetic transfinability. So we want to compare the strength of these axioms, ask if they're needed for some of these principles that we looked at from last time. And we want to come up ideally with a model in which these guys are true, but where this guy is false. But before we can do that, we actually run into a problem, which is what base theory should be used. So remember, whenever we try to do a reversal in the context of a reverse map, we throw away most of the axioms except the base theory. But the idea is that the base theory is supposed to be some theory that's strong enough so that the theorem still makes sense. So I want to argue that we have to think a little bit about what is going to be enough to make theorems about Borel sets make sense. All right, so this is just a repeat of the definition of Borel set in reverse math. So a tree, such as what I drew over there, is called well-founded if there's no infinite chain down here. So in reverse math, the Borel set is given by a code for a well-founded, countably branching tree that's labeled with intersections and unions. And so that's sort of the thing that that we use to represent the Borel set. So suppose that we have a Borel set, and we want that Borel set to make sense. And what I mean by make sense for a Borel set is like it is trying to represent like a subset of the infinite sequences. So for every infinite sequence, you want to know whether it's in the Borel set or not in the Borel set. Right. So if you're given a certain sequence, how do you tell if it's in or not? Well, there's sort of a procedure of sorts that you use. Right? You can say, all right, if you have a Borel set that's actually just like one of these like leaves, you can just check whether X is in there or not. Right? So that maybe the stuff that leaves is very simple, maybe it's closed stuff. And then if you're adding a union node, then X is in there, you can only if X is in one of the components that would have a union, similarly for the intersection. Because that's how you tell it's inductive. Oh, it's inductive. It's inductive. It's inductive on possibly like a very large order. So that means that in general, if you have some X and you want to figure out whether it's in a Borel set or not, the thing that you have to do in order to figure out whether it's in or out, actually at the most naive level, uses arithmetic transfinite. And that's a problem because if we're trying to come up with a model of Borel sets have property of error, blah, 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 that where ATR fails. We don't really want ATR to fail just because Borel sets like cease to make sense. That wouldn't be very satisfying. So we still want Borel sets to make sense. But the problem is that we may need ATR in order to carry out this process. So the object that you get from carrying out this process, we call it an evaluation map. Right, so that would be a map that would just assign to every single node making up the code for the Borel set, but it's there. X is in this, it's in this. So let's say this is the intersection, so it's in here, it's there. All right, so in fact, together with some co-authors, we were able to show that ATR is actually equivalent to the statement that anytime that you have a tree like this, there is something that you know whether it's in or out of the set. Okay, so this seems like bad news. It seems like ATR is sort of needed to make Borel sets non-vacuous. But ATR already proves the two things that we're trying to distinguish. So we really can't use ATR as our base theory if we want to succeed in this goal. Right, so the solution to this is given by what's called a completely determined Borel set. So basically, what we do is we just define the problem. So we say a Borel set is going to be called completely determined if, just by accident, for every X, we know whether that X is in or out. All right, so this is a situation that's like a little bit similar to the situation with the well order. All right, so you have a model, and that model has in it something that is a Borel code. And then that model also has a bunch of stuff in it that might be in or out. And if a model just happens to have, for no reason, just by luck, all of the evidence needed for every single one of the elements to know whether that element is in or out, then the model is going to say, oh, this Borel code is completely determined. So I'm going to consider it like a real Borel code that I want to talk about. And then there will be other codes, like things that are well-founded, they're labeled, but in the model, there's some stuff that the model doesn't know whether it's in or out. Well, the model will just say, just ignore that. That's not a completely determined Borel set. I'm not going to consider it, like when I talk about Borel sets in my theorems. Right, so in other words, we're going to take theorems about Borel sets and just restrict them purely to the things that actually look like well-behaved Borel sets. All right, so then we can define the principles. Every completely determined Borel set is a property of pair. Every completely determined Borel set is measurable. And both of these statements are now well defined without assuming ATR. So now we hope to create, get those two models, or to create some model where those Borel sets are measurable or have the property of pair, but where ATR is not happening in that model. There are a few slides that were going to be in this tutorial that are actually on Friday's tutorial. And so we hit the 50-minute mark. So let's skip just a few things that we'll do next time and say that what we got through this time was talking about reverse mathematics, what it is, arithmetic transfinite recursion, the main axiom that is like featuring in our questions, separations, which is the thing that we want to do between ATR and our theorems about, well, ultimately maybe our theorems about the Borel combinatoric stuff. We talked about hyperarithmetic sets and reductions because type is sort of this important omega model that is kind of not a model of ATR, but it's like related. And we talked about Borel sets in reverse math, how they're represented, and the need for making a slight modification to how they're represented in order to make this quest make sense. All right, so next time we'll talk about a pseudo Borel sets, which you might be able to guess what that is, as well as just then what is, so I'll give a small spoiler just to say that we are going to be able to make those models that separate every Borel set is measurable and the rest that is the property of pair and ATR, all from. All right, so that's the end of this training.
I think we've got time for maybe one quick question.
So there is direct proof that every analytic set has a property of pair. And then, so how does this relate to this? I mean, you don't need to do this inversion on the order.
So the proof that I know for every analytic set having the property of pair is a little bit complicated. I didn't see how to prove it using the ATR. We could talk about that after.
That was quick. So another question. All right, let's thank them again, and then we'll be back in 5 minutes. Right, so I've got the second tutorial definition by all of that.
Okay, so thank you very much. And we are going to continue with the tutorial. So, well, first of all, I wanted to write again the definition of construction scheme that we saw yesterday. Construction scheme, it has a decomposition. Well, F is a construction scheme, it has a decomposition Fk, K, and omega. So we start with singletons. The family is cofinite in omega 1, in the finite subsets of omega 1. And each element of rank K has size Mk. If I take any two of Fk, the intersection is an initial segment for both of them. And if I take any element in the of rank K plus 1, then I can find Nk plus 1 many elements of rank K that form a delta system, whose union is F, and the root has size Rk plus 1. Okay. And Esteban proved that this construction scheme exists. And another notion that we saw yesterday, if we take any two finite subsets of omega 1, then by VEF, we mean the only increasing bijection from E to the first of the first, second of the second, and so on. Okay, yeah, so this is what we did yesterday. The main notions. And now we want to see some applications. So applications of construction schemes are obtained as follows. So yeah, the purpose of construction schemes is to build objects, structures of size omega 1. So yeah, we want to do that and fix a construction scheme of some convenient type. Okay, so this is how we start. We find B, a forcing notion consisting of finite approximations of the desired structure. So I will not require force. Well, you do not need to know forcing for this, but it helps. But okay, so then if you do not know forcing, it's just I want to build some structure, and then I will have some set of finite approximations to that structure. Now, we order these approximations okay. Now, for every element in the construction scheme, I'm going to associate an element of the force, a finite approximation. And I will do it in the following way. If I take two elements in the construction scheme and E is a subset of F, then PF is a better approximation of EP, which we not like it as reinforcing. Well, it's some convention is that the smaller condition is the better approximation. So the bigger the element of the construction scheme gets, the better the approximation I have. Now, if I have two elements in the construction scheme of the same rank, then they must be compatible. Compatible means that there is a common lower bound, or that the approximations are compatible, that they can be combined. And moreover, they must be coherent in some sense. What will coherent mean? Well, it will depend on the problem, but we are working on. But we need some notion of coherence. Now you look at the structure generated by PF with F in F. And then, yeah, if you want to think of in terms of forcing, I constructed a filter for the forcing of finite approximations. So I use it to generate some kind of structure. And you know how that works for the problem you're working on. Okay, so this is like a general idea. We are going to see an example. So, okay, yeah, this is a line. Originally, I thought of constructing a Hausdorff gap and an arrow shine tree, but when I was writing the gap, I thought that that will take me the 4 hour. So in this lecture, we will construct a Hausdorff gap. And well, later in the slides, I can write the proof of the arrow shine trees. So if someone wants to see it, well, you can ask me for the slides. And also, well, these constructions are also in the physics of Fulgencio Lopez, which was a student of STEM. Okay, so we are going to construct a gap. Let me remind you what is a gap. So take subsets of omega, A and B. We say that A is almost containing B. Okay, what is that A is containing B? A is containing B means that every element of A is in B. Well, now almost inclusion is that happens, well, maybe there are just finitely many exceptions. Finite, it's finite, it doesn't count. A is almost subset of B. If the guys in A that are not in B, it's just finite. Okay, so now we say that G, which will be a sequence A alphas and B alphas, is a pre-gap if it looks like this. So the A alphas are increasing with the almost inclusion, the B alphas are decreasing, and each A is less than each B. Yeah, so they look like this, like they are like converging somewhere. And we say that this is a gap if there is no C such that I can put in between. There is no C that almost contains all A alphas and is contained in all of the B alphas. Or in terms of the drawing is, you cannot put something here that is in between. Okay, so now this is the definition of gap. Usually it's called an omega 1 gap, but yeah, since those are the only gaps we will be talking about in this lecture, we just call them gaps. And they are very concrete objects that show that P omega mod phi is not complete. It's not a complete algebra. Why? Because if the algebra was complete, I could just take the minimum of the A alphas, since A alpha is less than all of the bits, I could put the supremum in. Okay, so now a very remarkable theorem of Hausdorff is that these things exist. And it's really impressive because, well, the point is that if you have CH, it's very easy to construct. You have only omega 1 many subsets to take care of. You do a recursion of omega 1, you have omega 1 many steps and omega 1 obstructions to solve it in omega 1 many steps. That's easy. But the point is that what if the continuum is very large? And so if you have worked in cardinal invariance of the continuum, which is more or less, well, it's a lot of what I do. One gets used that everything is consistently bigger than omega 1. But this surprisingly, so you can look at the least size of a gap, This looks like a cardinal divided with a continuum, and usually those things tend to consistently or the mounting action be larger than omega 1. But surprisingly, in this case, there is one instance, and this was the overcast. And the usual proof, like you can read it in the discovery book, is by a recursion of size omega 1. You are constructing the gap with countable many, with countable approximations. Now we will prove this theorem, but using construction schemes. So one of the things that, I told you before, it was really impressive for me when I started learning this topic, is that the gap will be constructed in omega many steps. So it will be a recursion, but not of length omega 1, but of length omega. Well, of course, if you are very picky, it's a recursion of omega 1, but having as a parameter the construction scheme. And the construction scheme is constructed in omega 1 many steps. So you could say at the end, you do it in omega 1 many steps, but using this as a black box, or as a parameter, you do it in omega many steps, which it's very funny for me. Okay, just we're going to focus on constructing that thing, but just let me mention why gaps are important. The thing is that gaps are very important when you are studying or trying to embed structures into the omega 1 field. And gaps represent possible obstructions that we can encounter. So let's just say an example. For some reason, well, I have a linear order of size omega 2, and for some reason I want to embed this in the omega 1 field. Of course, yeah, we have CH, there's no chance, but let's say we don't have CH. So let's say I'm working on some problem and I need to embed this partial order to the omega 1 field. And I will go to try to construct the embedded recursive. So what could go wrong? It could happen that in the omega 1 many step. So let's say that in the omega 1 many step, we have defined the embedding F star that goes from the first omega 1 many into P omega, and like a very, very bad luck, we have the following. There are two uncountable subsets of omega 1 in the partial order. So let's see. This blue one goes to this blue one, the red goes to the red, and it turns out that in the image they form a gap. Okay. So we have these two guys, I send them to the embedding I'm constructing, and I have a gap. Okay, but now, if I look at the P omega 1 element, so far the embedding goes to the P alpha with alpha less than omega 1. Look at where P omega 1 is. And it turns out that it's between these. So I want to extend the embedding in order to say where this guy will go. But this guy has nowhere to go, because if it's an embedding of partial orders, this guy should go here in between. But this is a gap, so there's no one in between. So this means that I failed. I was trying to construct an embedding, and if I run into this equation, then I fail. So these are obstructions that you find. So This is just an example of precisely an obstruction you find when you're trying to. So yeah, but I said a star cannot be extended to an end. So our attempt to embed L into P omega naught infinity. And just well, this is just not some silly scenario that I invented to try to make gaps look good. So like if you look at the partition problems book, it is proved that PFA implies that 2 to the omega 1 does not embed in P omega naught phi. And the proof is precisely is this idea. You try to do an embedding, and it turns out that you have exactly this situation happens. Here you have 2 to the omega PFA. Here you have 2 to the omega 1, here you have the omega naught phi, and here you find something that goes to a gap, but that in this field. So this is a real situation that happens. So yeah, so gaps are very useful. And also there are a lot of work I think we started, it was Weber around Gardner, which it was on the other side, like, okay, so I'm like building my embedding generically, and so I don't run into problems, embedding stuff in P omega naught phi. So yeah, so there's a lot about this. Okay, but now maybe if you just learn the definition of gap, now I'm going to change it. So yeah, so new definition of pre-gap. So now a pre-gap will be again A alphas, B alphas, the A alphas are increasing, the B alphas are also increasing, and A alpha intersection B alpha is. And we say that this is a gap if there is no C, such that A alpha is almost contained in C for all alpha, or B alpha intersection C is finite for all alpha. Or in drawings, it means that there is no C I can put here. So in the drawing, it would be it's bigger than all of these and almost adjoined with all of these. So, okay, I changed the definition of gap, but these two are essentially the same thing. So one pass from one definition to another just taking complements of the deep one. So it's essentially the same thing, and in terms of existence, which is what I want to do, it's the same. So from now on, gap refers to this new meaning, and we are going to construct a gap in this text, which is uses one in the other. Okay, so now fix a construction scheme, but I will fix it mk plus 1. The n will be always constant 2. So what does this mean? The n was how many I'm gluing. How many I glue of the fk to get to fk plus 1. So then it means that every element in fk is the union of just 2 elements. Every element in fk plus 1 is the union of just 2 in fk. So it's like the C plus 1. Okay. So now, as we said, we're going to build a gap. So we start with the natural forcing or forcing in finite conditions to add a gap. So if you have previously, well, especially if you know forcing, if you just say, okay, I want to add a gap with finite conditions, and it's, yeah, if you think about it, you will get precisely this. Okay, so then the conditions, the elements of P are X and tuples X and a P with P. But X is a finite subset of omega 1 and n domain. X could be referred as the domain of P, and n is the height. AP will be a sequence A alpha P with alpha next, and BP is a sequence B alpha P with alpha next. I want all of these to be subset of n, this n, for every alpha next, and I want them to be disjoint. So let me just. So I'm approximating these guys, the alpha, the A's, and the B's, but with finite pieces. So if you want to look at the, yeah, so this is the draw. Here we have omega 1, omega. Choose finitely many guys in omega 1. This will be the domain of P. Choose a height, natural number. And now, in here, put the blue ones are the A's, the red are the B's. Put any set you want in here. But as long as the corresponding A is disjoint with the corresponding B. But from that, you do whatever you want. Okay, now the order. If I have conditions P and Q, I say that P is less than Q, which means that P is a better approximation than Q. If the domains get bigger, the height gets bigger. The A alpha, the point is that I'm preserving what I have so far. I'm just taking finite extensions. If I have an alpha in X cube, A alpha Q is A alpha P intersection NQ. Remember that A alpha Q was a subset of NQ. And B alpha Q is B alpha Q intersection NQ. So, yeah, the A alpha P's just extend are n extension of the Q's. Now I want to build a precap. So it's if I take two alt guys in the alt domain with alpha less than beta, then every new thing in A alpha P should be A beta P, and every new thing in B alpha P, this is wrong. This should be B beta P. So just the point is that I'm not promising that everything new in the A part of alpha is contained in the A part of beta, and everything new in the B part of alpha is contained in the B part. Yeah, so I'm going to put the conditions here in a moment, but if you haven't seen that this morning, maybe it was a lot at the moment, but just it's really the natural thing to do to add a gap with finite conditions. Okay, so now let's go back to the idea. We say that the idea is to find a forcing consisting of finite approximations. Okay, we've done that. Now the second step. For every guy in the construction scheme, I want to find a condition. So to every guy in the construction scheme, I associate a condition with these properties. The bigger in the construction scheme I get, the better approximation. And if two have the same rank, then they are compatible and coherent. In some sense. Okay, so now to every element of the construction scheme, I'm going to associate a condition, but also I'm going to define a sequence and case with the following properties. The NK is an increasing sequence of natural numbers. Okay. Now, the domain of the condition PF will be F, and the height of PF will be NK, in case F is in FK. The domain of PF is F, and the height is NK. So in particular, all elements of the same rank have the same height. And for convenience, I'm going to write, if I have an alpha in F, I write A alpha F instead of A alpha P sub F, and B alpha F instead of B alpha P sub F. Now, this is the condition I said before. If I have two elements in the construction scheme and E is a subset of F, then PF must extend PE. If F is bigger than E, then PF is a rare approximation of PE. Now, take any two elements in FK. I want the conditions to be compatible. This is what I said before. But now the coherent part, which is the new one. I want that if you take alpha in F and phi is the increasing bijection, then A alpha F is A phi alpha of E, or B alpha of F is B phi alpha of F. So alpha goes to phi of alpha, but then the A is the same, the A for alpha is the same as the one of A of B alpha. And the one of B alpha is the same as B of E alpha. And then this should be B. This is the coherence. So, in some sense, this means that the A's and the B's only depend on the position. So, the first guy in F, the A of the first guy in F looks like the same as the A of the F of the first guy in E. The second one of F looks the same, the A of the second one of F looks the same as the A in the second one of E. And so on. Here I just rewrote the conditions if you want to read them again. Using sequence, the domain of PF is F, the height of PF is NK. If you go up the construction schemes, you get better approximations. And if you have two of the same rank, they are compatible, they have a common approximation, a common better approximation. And the A's and B's only depend on the position. Okay, so we are going to define these items recursively. Best case, K equals 0. So I just say, okay, and 0 is 2. And now choose an F in S0, 0. And well, in the construction scheme, we said that the first level is all singletons. So F is on alpha. So I know PF should be singleton alpha 2. And now I need to say who A alpha F is and who B alpha F is. just say, and it can be whatever you want. Just say, the only restriction I have is that they need to be disjoint. So let's say I put 0 in A alpha and 1 in B alpha. Even if you want them to be empty, it's okay. Just as long as they are disjoint. And okay, so this is the first step. Now the recursive step. Assume we have defined NK and EE for all E in FK. We will now define NK plus 1 and PF for F in FK plus 1. Okay, so I'm just going to say NK plus 1 is NK plus 5. So I started with 2 and I'm just adding plus 5 each time. So hard to can compute exactly with this, but we don't do that. Okay. So take an F in F plus 1. So we know that F, there are two guys, F0 and F1 in Fk, and a root. Yeah, so F is F0 in F1. The intersection is the root size are K plus 1, this one model. And they look like this. Delta system, which is get take. Or as I prefer to it, is this wrong. F is this. So remember that the construction scheme I choose always has just 2 parts. The simplest construction scheme possible. Okay, so now it's better to draw what we're going to do. So we need to say who are the A, F, and the BF. So in this part, well, in this part I don't care, it's already frozen. I cannot change this part. What I'm going to define is what I use here to in these 4 guys. I'm going to do a little bit more than I really need to do, but just so that the picture looks more symmetric, but you can even do less. So, well, just the notation in the picture. This blue means that I will put a point. And the cross, it means that I will not put that point. So, for example, this means that the guys in here, I will put NK plus 1 in the area. And from the ones in here, in the BF, I will not put that point. Okay, so I just want the sets to be infinite. So I will say, okay, put NK plus 1 in all points, in all the guys. And since the A's must be disjoint with the B's, if I put one in all of these, then I say, okay, NK plus 1 cannot be in any of these. Good. Now I want the B's also to be infinite. So put NK plus 2 in all of the B's. Then you cannot put NK plus 2 in any of the A's. Okay. Now, in the root, I won't do anything else in the root. So in the root, I will always say just for simplicity, in the root say I won't put anything. So not in the A, not in the B. And now I will put nk plus 3 in all the A's. In all the A's of the first block. And since the A's needs to be disjoint in the P's, then that means that nk plus 3 cannot go in the P's of the first block. Now, oh, okay, the A's, okay, and now I will say that you don't put a point. Oh, no, yeah, it's better to finish first. And I will put the point in the piece of the second block. If I do that, then I'm forced to do not put that point in the A's of the second block. Okay, and now in the root, for simplicity, I never do anything anymore, so I don't put the nk plus 4 in the root. And I'm going to put nk plus 4 in all the P's of the first block. So that means that it cannot go in the A's of the first block. And I will put it also in the A's of the second block. So then it cannot go into the P's of the second. So this is what I do. So I like mathematics that are deep, complex, but look at giant drawings. Okay, I just do the same here, but it's right there. Okay, and just this is the explanation. If alpha is in the root, then alpha is okay. BA, it has, here is blue, so I put A alpha S0 and I put nk plus 1. And now everything is crossed, so I don't put anything else. For the B's, in here nk plus 1. I always start with what I have frozen before, and I only put this nk plus 2. Now, if alpha is in the first block, so I have blue here, so it means that I put nk plus 1 and I put nk plus 10. And for the B, this is a cross, I don't put it. I put nk plus 2. Here's a cross, I don't do anything, I put nk plus 2. And if it's in the second block, okay, I put nk plus 1 and nk plus 4 and nk plus 2. Here is a cross, I don't do anything. Nk plus 2, nk plus 3, and then I don't do anything. So it's clear. Are there any questions on how I define this thing? Okay. So, but now the point is the following. I take alpha in the first block and beta in the first block. Then these big points. Nk plus 3 is in A alpha F and is also in the B. So Nk plus 3 is in A alpha F intersection E beta F. And I forgot to draw the big points in this, but here there should be a big point and this should be a big point. Nk plus 4 is in A beta F intersection B alpha F. So, well, if you are familiar with gaps and you know these Cournot's freezing condition, which are exactly the Cournot freezing condition. So that's why it's going to be a. If you do not know, it doesn't matter. Because yeah, I will still prove it. But you know, that's precisely the motivation of doing that. So obviously, how I did it is not exactly, is not that relevant how we do it. I think in tensor space is different. But the point is this, that you have the switch. You have one guy in the A and one guy in the B. That's the point. You have this cross, the cross. Okay, and then this finished the recursive construction. And you can see that we define it precisely, it only depends on the place alpha is and so on. So, okay, so now, yeah, if you think of in terms of forcing, I define a filter for this forcing, and now I define the generic graph. So A alpha is the union of the A alpha F's, B alpha is the union of the B alpha F, oh, sorry, A alpha is the union of A alpha F when alpha is in F, and B alpha is the union of B alpha F when alpha is in F. So as an exercise, prove that this is a frequent. That's easy. And the point is that you really are using is that if you take any alpha and beta, at some point there is that the conservation scheme is provided. So this is easy. That is a free gap. What's more interesting is that it's a gap. We now prove it is a gap. So assume that there is a C such that it almost contains every A alpha, but it is almost disjoint with every B. Or I prefer drawings, there is a C that I can put here. Okay, so C almost contains each A alpha, and it's almost disjoint with each B alpha. So, for every alpha, we can choose a large enough L alpha so that it gets rid of the almost inclusion, almost disjointness. Find an L such that A alpha minus L alpha is contained in C, and B alpha minus L alpha is contained in the complement of C. Okay, so now we just use a counting argument. I have omega 1 many alphas. So then I can find an L, but then I can find 2, in fact, omega 1 many, but I will only use 2. Such that they have the same L. And up to L, A alpha up to L is the same as A beta up to L. And B alpha up to L is the same as B beta up to L. Okay, so then fix this alpha and beta have the same L, and the A's and B's up to L are the same. Now let K in omega be the first one, such that alpha and beta are in F. I know there is one. And in other words, this is the distance we defined before. The ordinal metric we defined in the previous lecture. This is the distance between alpha and beta. Okay, so alpha and beta are in F. And now I claim that alpha is in the first block and beta is in the second block. Why? Well, assume beta is in F1. So it could be I theoretically here, or also it could be that it's in here. beta. But alpha is less than beta. So then, if beta is in F1, alpha must also be in F1. So it means that both alpha and beta are in F1. But what was K? K was the distance. K is the minimal, the minimal, such that there is an element in the construction schemes that has both A alpha and beta. So in here, they both are in F1, and F1 has rank K minus 1. So that's impossible. Okay, and by the same argument, I say that alpha cannot be in F2. So if alpha was in F2, and again it should be in here or in the root, but then beta will also be, no, sorry, well, there's no, beta cannot be in the first block, but beta will be in the second block, and again, they will be in one of rank K minus 1. So that's impossible. So it means that alpha and beta, look, when I define the F, they, in this situation, alpha is here in the first block, beta in the second block. So then there is this pinpoint. That is in A alpha F and B beta F. So then we get that there is an I, the pinpoint, that is in A alpha and B beta. But here was S, but A alpha is the union of A and B, A alpha S. Okay, and now I claim that L is less than or equal to I, just to recall it. Up to L, just to recall it, I is in A alpha intersection B beta, and I also have that A alpha intersection L, sorry, this should be B alpha. They forget this one, and it's really this one. So I is in A alpha intersection L, which is A beta intersection L. So this means that I is in A beta intersection B beta, but by definition, A alpha and B beta are disjoint. This is a contradiction. And now finally, recall that A alpha after L is contained in C, B beta after L is contained in the complement of C, and now I is in A alpha and is bigger than L, bigger or equal to L. So I is in C, and I is in B beta is bigger or equal to L. So I is in. So I get that I is in both C and its complement, which is a contradiction. So then it follows that, yeah, so then it follows that this is a gap. And yes, as I said, usually this is done with countable conditions, but this is was finite and with omega many steps. And well, yeah, this will be the end of the one for today. I said there are other constructions, like it's also possible to do a Aron chain. And this was all in CLC. This exists without assuming any additional actions. So what we are going to do in the next lecture is adding a little bit more, like a consequence of diamond, and get other objects that do not exist just from CSC, like SLALM. So thank you very much.
Are there any questions? So I haven't seen the construction, like the previous construction of the house work out, but how much of, like, how many days years are the same? Is there some kind of common material core that stays the same? Or is it really complete?
What is similar is the, well, you make sure to have this cross thing, but yeah, but this must be common in all construction because it's equivalent. So you make sure of this, but that's because you must in all construction. So apart from this, really, yeah, they are completely different because so in house of construction there is some notions, some device you use so that you make sure not to get stuck. But yeah, I would say.
So if you have to do this, you have to not get stuck.
Yeah, yeah, but then apart from the things that you must do because it's an equivalent of that, I think they're like completely different construction programs. Yeah, really, none is the other in disguise. They are completely different.
Any other questions? All right, and then the last part of the tutorial will be on Friday. That's next again.